So chapter 2 is all about polynomials and rational functions. And the first section is all about quadratics, which are technically polynomials, some of the simpler polynomials. So what we're going to focus on today is we'll be looking at transformations with quadratics. We're going to be looking at 3 different forms that you can write the equation of a quadratic function in. So that would be vertex form, which you can see some notes for that down at the bottom of your page here. Does this look familiar to you from last year? This format of a quadratics equation down towards the bottom of your page there. Oh, am I frozen? I'm sorry. Thank you. This vertex form. Yes, great. We'll be talking about standard form. Standard form of any polynomial is just that ax squared plus bx plus c. There's also factored form, which we won't get much into today, but we will be using factored form a lot as we explore polynomials in the later sections. But our main focus today is going to be on analyzing quadratics and looking at equations in vertex form and in standard form and pulling information about the quadratics from that. And then also changing from standard form into vertex form, which is where we're going to get into completing the square. Do you guys remember doing completing the square last year? So one of the contexts that we will be practicing that this year is with our work with quadratics going from standard form to vertex form. So let's start by just doing a quick graph. We got f of x equals x squared. You guys should feel pretty confident filling out that table and graphing that parent function. So go ahead and do that for me right now. We're just squaring each of these x values to get our y value. And then graph that. And that should be that nice familiar shape of a parabola you're used to seeing. And let's take this opportunity to practice with some transformation work. So you guys practiced, I asked you to practice some of this in your assignment, one of your assignments last chapter. What I'd like you to do with this problem down here is to tabulate our parent points. So our parent function would be y equals x squared. Those key parent points are x values of -1, 0, and 1. And then let's do some transformations on this parent function until we arrive at this equation. So I would love for you to do as much of this on your own as you can. We practiced this in several examples in class, and I asked you to do this on, I think, 6 or 8 different problems in the assignment. Many of you did not, but let's take this opportunity to go ahead and practice. So what I'm asking you to do here is to do a transformation to show what that does to the table, what it does to the equation, describe the transformation in between until you get to the final one. Do you guys remember the cheat code I taught you about order of doing transformations? If you don't, I'll remind you. If it's in a format where the x does not have any coefficient on it, then it's really easy to do to figure out what order to do your transformations. And the simple rule is do all of your shifting last. If you do all of your shifting last, you won't have to worry. Everything's going to be nice and straightforward. So if I were doing this problem, I would probably start with this 2 on the outside first, and then I'd take care of my shifts after that. So my first step would be to multiply my whole thing by 2. Do you guys remember what kind of transformation that would be called? How would we describe that? Vertical stretch, because it happened on the outside, by a factor of 2. Which coordinates would that affect, the x or the y coordinates? Vertical stretch is going to affect x coordinates or y coordinates. Anything vertical is going to affect the y coordinates. So the x coordinates are going to stay just how they were. And the y coordinates will all multiply times 2. 2, 0 times 2 is 0, 1 times 2 is 2. Okay. Now you got 2 more transformations to do. Go ahead and do those last 2 on your own, please. Let me know if you need any assistance with that. We'll come back together and compare answers. Once you get your last table, then go ahead and graph that, please. I chose to do my horizontal shift first and my vertical shift last, but if you switch the order on those 2 things, it should not have mattered. Your final table should be matching mine. Anybody have any questions about those transformations? We feeling pretty confident? We're going to be doing the same thing every time we introduce a new function. So you'll have some problems, I believe, in your assignment where it asks you to do transformations and graph, and this is what I'm hoping that you will do. If you want to graph every step as well, that could be beneficial just to get a visual on what's going on. I don't require that, but do it if you think it'll help you. Any questions before we move on? All right, so the cool thing about vertex form is it makes it really easy for us to find the vertex just by looking. You know, our vertex is usually at 0, 0. Because of this format, because it's in this format, we know that that's going to be shifted. That shift's going to occur last. So 0, 0 is not going to move for anything except for shifts. And so whatever these values are can tell us exactly where the vertex is going to be. So this is the same problem, but if I go back in time to before I worked out where this vertex was going to be by doing transformations, I could much more quickly and easily find the vertex by just looking at this +2 and this -5 and saying that my vertex is at -2, 5. -2, -5, excuse me. And then the axis, remember, is that line of symmetry that goes through the vertex. It's always going to be a vertical line for the parabolas we will be dealing with. So it will always be an x equals equation like every other vertical line is. Since it must go through the vertex, it's got to have the same x value as the vertex, x equals -2. Is this pretty familiar to you from last year? You guys did a lot of work in vertex form, I feel like. Good. Okay, so we're going to switch from vertex form over to standard form now. Any questions before we do? All right, let's do it. So standard form, not quite so easy. However, there is a way that we can look at an equation in standard form and come up with the vertex and the axis. Just requires a little bit more work. So there's a formula that tells us how to find h and k. Remember, h and k are the coordinates of your vertex. The h coordinate we get by applying the formula opposite of b over 2a. And I feel like you guys are really familiar with that from last year. And then what does this mean? K is f of h. What are we going to do to find k? We're going to plug in h into the function. So once we find h, we'll plug that back into the function, and that'll help us find k. This is something really interesting that I just kind of, it took me way too long to recognize this. This is kind of came to me today. Do you guys know the quadratic formula pretty well, right? Have you ever recognized that this is part of the quadratic formula? Did your teacher ever point that out to you? Oh. That part I recognize, but I think this is kind of interesting. So if this is the x-axis, you don't need to write this down, by the way. And I have a quadratic function. I've got that parabola. My vertex is going to be here. And that value, that x value of that vertex is going to be at the opposite of b over 2a. Do you guys know how far that x value is away from this x-intercept right here? It is the square root of b squared minus 4ac all over 2a. That's how far away it is. Does that look familiar? That's the other half of the quadratic formula, right? And why is it plus or minus? Well, because there's an x-intercept to the right and there's an x-intercept to the left. So this is kind of the center, and then that plus or minus tells us how far we have to go to the right and to the left to find those x-intercepts. I thought that was pretty interesting. Never made that connection before in my life. So anyways, extra information. Let's do this example, and I'm going to try and do a better job than I did first period today. We got halfway through this thing before I realized that I made a pretty fatal mistake right at the beginning. Do you guys see the tricky thing about this example? Yeah, I totally missed that the first time. We were like almost done with this problem, and someone was like, hang on, this thing's out of order. So I looked at this and I thought A was 7 and B was -2 and C was -3, but it's not, is it? So let's rearrange this thing. We like to see our x squareds first, and then our linear term, and then our constant term. I don't require that you write down A equals -2 and B equals 7 and C equals -3. If you want to, if it helps you, feel free to do that. If you're able to just look at the standard form and pull those numbers out for this class, that's fine with me. So let's find our vertex. We're going to find H, which is the opposite of B over 2A. B is 7, A is -2, so we're looking at -7 over -4. Let's call that 7/4. All right. We still need K, but we've got a lot of information right now. What I know at this point is that my vertex is at 7/4 comma something. What else do I know? We know the axis, right? The axis is x equals the x coordinate, so x equals 7/4. They also wanted us to write an equation in vertex form. We have a portion of that equation right now. Y equals, vertex form is something times x plus or minus something squared, and then plus or minus something at the end. And we know what that horizontal shift is going to be at this point. It's 7/4, so we need minus 7/4 here. Do you guys know, while we're here, what this is going to be in front? Maybe be helpful to look at this equation up here. It's going to be -2, yeah. We're going to need a -2x squared, and this, if I were to multiply this out, it's going to be x squared minus something x plus something. So this is going to be -2. The a value in standard form matches this value that's out in front here. So all we're looking for is the y coordinate of our vertex. That'll tell us what our vertical shift is. And to find that, this is the tedious part. To find that, we are going to need to take our function and put 7/4 into it. So -2 times 7/4 squared plus 7 times 7/4 minus 3, and come up with a nice, neat answer for that. And I don't know about you guys, but it's been a long week. My brain's a little frazzled. You okay if we use some technology to help us with this? We can all do this by hand if we needed to, right? But we don't need to. So let's give ourselves a little bit of a break here. I'm just going to type this in. Now, these instructions down here, I need to take these out of my notes. I've been using these notes for a couple of years, and this is way more complicated than we need to do. I'm just going to type this in exactly as it is, and then I'm going to put something special after it to tell my calculator I want it to spit out an answer that is a reduced fraction. So go ahead and type it in to start, just like it is, 7/4 squared plus 7/4 minus 3. Oops, I lost a 4 there. Some of you already know this little trick, but there is a magical thing that your calculator can do. Did you know that it will turn any rational value into a reduced fraction for you? Like if I hit enter right here, it gives me that, that's a fine answer. Actually, that's a pretty nice rational value because it's a terminating decimal. We're going to deal with stuff where it's going to be something over 7. So we don't want to round if we're giving exact answers. Do you know how to ask the calculator to give this to you as a fraction? Oh, you got to see this. This is one of the cooler things about these calculators. It's under the math button, and it is the most popular function, so they put it right up at the top. Do you see arrow frac? If you hit enter here, that's going to it's going to bring this up, and basically this is saying, hey, calculator, take that last answer you gave me and turn it into a fraction. If you hit enter, it'll do that for you. It comes out to be 25/8. Isn't that amazing? What a wonderful thing. I'm not afraid of fractions, but they're tedious and prone to errors, so it's nice to have a little backup, or a check at least. All right, does anybody have any questions? So far we've talked about vertex form and transformations. You guys seem fairly confident with that. Do you feel confident that if I gave you an equation in vertex form like this, you'd be able to look at that and very quickly tell me what your x and y coordinates for your vertex are, find the axis, okay? Do you feel confident if I give you something in standard form that you could use some formulas to figure out what the x and y coordinates of the vertex are and the axis are? Great. The next thing we're going to do is practice going from standard form into vertex form. There's multiple ways to do that. We actually kind of just did it here using these formulas, but I want to do it a different way called completing the square. And we're going to, I'm going to step you back to some background information about completing the square before we do this, because this isn't the only place we're going to use this. And I want you guys to understand, I feel like my students coming from Algebra 2 typically know the process for completing the square, but maybe not necessarily why it works or how it works. And the why is going to become important for us later on, okay? So here's the deal. There are these things called perfect square trinomials. Have you guys heard of those before? It's something that we usually do in Algebra 1, but we haven't for the last few years because of the whole COVID and we just haven't had as much time. So the whole idea of a perfect square trinomial is there are these special trinomials that fit into this pattern. You've got something squared for the first and last things, and the middle term has to follow the rule that it's 2 times the b times the x. Sometimes you use a's and b's. This should look familiar to you for those who know the shortcut for squaring a binomial. This is kind of the backwards version of that, right? And it turns out if you have a perfect square trinomial, if it fits the rules for this thing, then that's really easy to factor. You don't need to do an x in a box or anything like that. It's just going to be x plus or minus whatever that other thing is. Throw some parentheses around it, slap a square on it, and you're all good. Okay? So let's start by practicing just figuring out whether some trinomials are perfect square trinomials. When I look at this, if I want to test, I'm first going to look at my first term and ask myself, is that a perfect square? Yes, it is. That's x times x, right? And I like to just write down the thing that's being squared to get it. That's x times x, and I'll look at my last term and ask the same question. Is that a perfect square? What would you multiply by itself to get 9? 3. Yes, that's a perfect square. And then there's one more rule, and the other rule is that that middle term must be the result of multiplying these two things together and times 2. So 2 times my other two things. In this case, my other two things were x and 3. If I multiply 2 times x times 3, is that going to get us that middle term? Yes. So that means it is a perfect square trinomial, which means it will factor into, it's going to have this x and this 3 in it. And then the sign in between them is going to be determined by whatever this sign is. So it's going to be a plus. And I'm missing my square. So I don't need to go through and do an X box or anything like that. I know that it's going to factor because it's one of these special trinomials. All right, so check this second one for me. Is this a perfect square trinomial? We've got a perfect square here, x times x. We've got a perfect square here, 5 times 5. The big question is, does the middle term equal 2 times those two things multiplied together? If I multiplied 2 times x times 5, is that going to get us that middle term? Answer is yes. And we're disregarding the minus here. And since that is, then great, then we can go ahead and factor it. It's going to have an x, it's going to have a 5, and this time, because it's got a negative here, there's going to be a minus in between. So perfect squared trinomials are convenient. They're special because they can be factored into two identical factors being multiplied together. You guys feeling okay so far? Okay, so that brings us to the concept of completing the square. So if I were to ask you to look at this right here, I'm just covering up this part of it. It's x squared minus 16x. Is that a perfect square trinomial? It is not. It's missing that last term. Could we force it to be a perfect square trinomial? Well, it does have x. That is x times x, right? So if we could be clever and pick the right thing here, so this is a perfect square, and so that 2 times x times whatever that thing is, then we could force it to be a perfect square. We are completing the square. Okay, right now it's incomplete. It's not a perfect square trinomial, but I could make it a perfect square trinomial by doing that. So kind of think with me, if I'm trying to get this to equal 16x, what does this number need to be that I'm missing here? What's the thing I'm going to square to complete this? 2 times x times what's going to give me that 16x? Help me out. 8, yep. So that means that this thing is going to be 8 squared, which is 64. Now we have completed the square. We have forced this to become a perfect square trinomial. So it can be factored as x minus 8 quantity squared. Okay? So that's why this is called completing the square, because we're literally trying to figure out what is that extra thing we can put in to make it one of these special trinomials. Now, when you learn this back in Algebra 2, they probably, they may not have gone into that detail on why it works. They probably just gave you a process, but that process is basically what we just talked about, right? What did they tell you to do? They told you to look at this negative 16, and you had to do 2 things to it to figure out what the 64 was. Do you remember what those 2 things were? What did you do first to complete the square? You guys said you do this. Say it louder. Divide it by 2. That gets us negative 8. And then what did you do with that negative 8 to come up with the 64? You squared it. Okay, which is kind of what we just did a second ago. We weren't thinking of it in terms of a process. We were thinking of it in terms of what number do I need here to make this a perfect square trinomial. That's why this process works. We're dividing it by 2 to figure out what this number is, and then we're taking that number and squaring it. Okay? So let's just practice completing the square here. Let's use the process this time. So take this coefficient here and divide it by 2. When I'm dealing with fractions, I think of dividing by 2. Instead of dividing by 2, I think of it as multiplying times a half. 3 over 2 times a half would get me 3 over 4. And then square that. 3 over 4 squared would be 9 over 16. So what do? We just took this incomplete trinomial and we completed it so that it would be a perfect square. And because it's a perfect square, now we can conveniently factor it into x, and this should be plus 3 over 4. This number here is always going to appear inside of your factors. Okay, are you guys remembering this process at this point? Feeling okay about that? Okay, what is this? I keep forgetting we have an assembly today. 37, we're doing great. So completing the square is useful to us in a couple different contexts. We are going to use it right now to go from standard form to vertex form, but there are a couple other ways that we're going to be using this in this course. So we're going to go into this particular context, but before we do, I want to remind you that the trickiest thing for me about completing the square is making sure that we keep things balanced. So we're going to be working with these expressions, and we don't want to change the expression. So we got to keep in mind that when we start sticking extra stuff into an expression, we're changing its value. If we want to keep that expression the same, because we're focusing on a particular function, then any place where I add a 64 into that thing, I also need to subtract a 64 someplace as well. Otherwise, I'm changing it. I'm changing the value of that expression. So let's flip the page and look at another example here. So let's say we're trying to take an equation like y equals, I don't know why I didn't put my y equals in here, f of x equals x squared minus 6x plus 12. That's in standard form. We want to force this thing into vertex form. In order to do that, vertex form always has something squared, so we're going to need a perfect square trinomial so that we can factor it. So we're going to go ahead and complete the square. So here's how I kind of think my way through this. So I focus on these two things as the beginning for my perfect square trinomial. I'm going to try and create my perfect square trinomial here. This is going to be the thing that's going to factor into my factor squared, okay? So at the beginning, my thought is, okay, let's just move the 12 off to the side. And I left a little space because I'm going to be adding something else in here to complete the square. The question that I have for you is, what am I doing out here? What's that all about? Say it again. We're doing the opposite? Because why? To keep it even, yeah. So if I put some number in here, let's say I put 500 in here, that's not going to be helpful to us. But if I stick a 500 in this blank right here, suddenly I've changed the original expression, haven't I? It's not the same function anymore. But if I put in a 500 in here and then I do a minus 500 out here, then it still is the original expression. Okay, so it's this opposite thing that you got to kind of keep an eye on and make sure that you're balancing. We can't just go throwing extra stuff into a function unless we someplace later on take it away. We got to keep it balanced to where it was before. Okay, so let's actually do this. Let's complete the square here using the method that you guys learned last year. We're going to take that middle coefficient. We're going to cut it in half to get -3. We're going to square it. And that's going to give us a positive 9 here. But I can't just add a 9 into this thing because now this thing is not the original function. As it is right now, if I don't put anything in here, if I were to simplify this, it's x squared minus 6x plus 21. That's not what we started with. I want to analyze this function. So let's keep this balance by subtracting that 9 over here, so that if I were to simplify this thing, it would be equal to the original expression. Once we've got that done, then we can go ahead and factor it. The whole point of doing this was to turn this into that perfect square trinomial, which makes it factor really simply into x minus 3, quantity squared. Remember, that number there is always going to give us our squared binomial. We've still got this 9 hanging out here. And to wrap this up, I'm just going to combine that 12 and that -9 together. And that will give us our vertex form. What do you guys think? Did you do something like this last year where you had to keep it balanced, you had to subtract it at the end? There are kind of different ways to manage this to make sure that things keep balanced. So this might look a little bit different from the way that you did it before, but something kind of similar, maybe? No? Okay. Are we feeling okay about it if it is new? All right, let's try something a little bit more complicated. This is where things get a little bit complicated. So this whole process where we divide by 2 and square, that will only work if we've got a trinomial where there's a coefficient of 1 on the x squared. That only works if my coefficient is 1. If there is a different way we can do this, if it's something other than just x squared, if it was like a 6x squared or something, there's a different method we could do to find this. It's much more complicated. So rather than deal with that extra complication, what we'll do is we'll just make sure that we only ever have an x squared inside here. So in a situation where there is a coefficient, we're going to factor that coefficient out. And that will get us back to that simpler situation where there's just an x squared. So when I look at this, my thought process is I'm going to set this 7 aside and focus on these two terms, and I'm going to turn these two terms into a perfect square trinomial. But I can't have that 3 sitting out front, so I'm going to factor that to the outside of my parentheses. All right, so what's that going to leave us inside here? It's going to leave us with just a 1x squared. That's what we wanted. And we're going to have a minus 4x after I factor that 3 out. And then I'm leaving space for that value I need to find to complete the square. Okay, we feeling okay so far? Now keep in mind, in a minute, I'm going to be putting some number in here, and if I do, that's going to throw everything off. That's not going to be equal to the same thing anymore. I need to make sure that whatever I do in here, we're balancing somewhere out here. So I need to take away something out here, but it's not as simple this time around because why? Let's say I put a 10 in here. That's not the right value to complete the square, but I can put anything I want in here. If I put a 10 here and I put a minus 10 out here, is that going to keep everything balanced? No, because why? Because that 10 is not actually a 10, it's a 30, isn't it? Okay, so if I want to keep things balanced, if I want to put a 10 here and a 10 here, the way I think of it is, let's make sure that whatever I put in that spot is being multiplied by 3 also. So when I set this up, I will always think about, okay, before I figure out what goes in here, let me figure out how to keep it balanced so that I'm also subtracting or doing the opposite. I should be saying the opposite instead of subtraction. You'll see why in just a moment. So would you agree at this point that if I put the same number in these two spots, that those things are going to end up canceling each other out? If this is a 10 and this is a 10, then we got a 30 and a negative 30. Boom, we haven't changed anything. Okay, it's not 10. Let's figure out what it is. So we'll take our middle coefficient, we'll cut it in half, we'll square it. Looks like it's going to be 4. All right, so that, I'm kind of annotating off to the side. That step right there is kind of these two things together. All right, let's factor it. This is going to be really easy to factor now that it's a perfect square trinomial. It's just going to be x minus 2, quantity squared. I've still got a plus 7 here, and then minus 12, and we'll just do a little combining like terms and we'll be all set. So final expression would be that. Yes. The assembly is still happening, yes, as far as I know. Let me pause. All right, we're going to get back to it. So just to remind you where we were, we're doing this completing the square thing, and we did have to factor something out. So I'm going to challenge you guys right now to try one of these on your own. This one is a little bit different. You're going to find there's a little bit of a quirk to this one that you didn't have to deal with up here. But much of it is the same. The difference this time is we're not factoring a 3 out. We're going to have to factor a -1 out at the beginning. But other than that, the initial steps are going to be exactly the same. So I want you thinking about, okay, I'm going to factor that -1 out. I'm going to leave some space. I'm going to make sure that I include my -4. I'm frozen. I'm so sorry. Thank you for reminding me. So I'm going to be factoring this -1 out. I'll leave some space to do my perfect square in here, and then let's make sure that we're balancing with opposites. And remember that term opposites is going to be kind of key for this one. I will be working this problem silently up here, so feel free to glance at the board if you need a hint. But I feel like you would be much better off to try and do as much as you can on your own rather than copying my work. All right, flipping the page. This is our last page, and you know what? I think we're going to cut off. We got 3 problems on here, but we're going to cut one of them off. You guys seem to be pretty strong with this. I'll be happy to, if anybody is interested. This is the one I'm going to cut off for today. But we should have some time after this. If anybody wants to work through this with me, I'd be more than happy to do that. But let's do this. So we're now going to kind of go a little bit further. We're going to, our goal is to analyze and describe the function. And for this particular problem, we're limiting that to vertex, axis, y-intercept, and x-intercepts. Eventually, you will also be doing things like end behavior, increasing, decreasing, local maxes and mins, is it odd or is it even kind of stuff with these as well. But let's just focus kind of on the key stuff for right now. So if I want vertex and axis, for me, the easiest way to do that is to complete the square. It's not the only way, but let's go ahead and do it because we're going to need practice to do it in some situations later on. So let's start there. Let's see if we can take this thing and turn it into an equation in vertex form by completing the square. So just like before, we're going to need to start by factoring because we can't complete the square the simple, easy way unless it's just an x squared. So let's factor this 3 out. Don't lose that minus 2. My most common mistake is I'll start completing the square and I'll forget about this thing out here. Now, my Algebra 1 students, if I asked them to factor 3 out of 8x, would tell me you can't do that, but you guys know better than that, right? You know you can factor anything out of anything, it's just sometimes you're going to end up with a fraction. So if I factor a 3 out of 8, and I'm going to get 8/3. And leave some space, and then make sure that you're balancing with some opposites so that we don't put something extra into this function. So, hello. How's it going? Good. Gotcha. Is this like a right now thing? Okay. Yeah, I'll put the notes online. You got it? Yep. All right. We got some fraction stuff to do here, but that's all right. 8/3, cut it in half. I'll give us 4/3, square it. 16/9. Does that sound right? 16/9. And then let's simplify that. So this will factor now. And you know what? It's been a long day. I'll let the calculator do the heavy lifting here. -2 minus 3 times 16/9. Math frac. 22/3. Pause here for a second for questions, and if for folks that might still be working to get caught up, any questions? Are you spotting any mistakes up here? I've made quite a few today. We good? All right, so go ahead and find the vertex and axis. That should be pretty easy for us now. Now that it's in vertex form. We're also going to be looking for x-intercepts and y-intercepts. We talked about this in chapter 1 when we were analyzing functions before. Do you guys remember how to find x-intercepts and y-intercepts for any function ever? Let's do the y-intercept first. I always find that easiest. How do we find a y-intercept? It's all about zeros. Find the y-intercept, 0 in for x. Where the y-intercept is f of 0. So if we plug 0 in, and I could do it in here, but I feel like this would be an easier format, right? So f of 0 is, well, 0 plus 0 minus 2. That's -2. So my y-intercept is at 0, -2. Nice. That was easy. Do you remember how to find the x-intercepts for any function ever? You're going to set y equal to 0. So we're going to set this whole function equal to 0. So 3x squared plus 8x minus 2 equals 0, and then we need to solve that. We have 2 different methods that we've talked about so far this year for solving that. One would be to factor it, if it does factor. And the other is everybody's favorite, quadratic formula. It doesn't factor. Hooray! We get to do quadratic formula. So go ahead and practice your skills here. Good opportunity to practice with quadratic formula. $64, $24, $88. $16, I don't think so. Why did I circle that? That's not my answer. I almost lost myself half a point on that test question. I forgot. I got so busy using the tool of the quadratic formula, I forgot what I was trying to do with it. We were trying to find x-intercepts. So hopefully when you write your final answer, you're going to write it as coordinates and a point. X-intercepts are points, and points deserve the respect of an x and a y coordinate. I would also accept if you didn't want to write out both versions, if you just wrote out one of them with a plus or minus, that's fine, but I need to see that comma 0, and it needs to be inside of parentheses, please. How are you guys doing with that quadratic formula? Is it coming along? We'll be using it a bunch. All right, we got our x-intercepts, our y-intercepts, our vertex, our axis. We're pretty good here. I want to show you one thing. I don't know if you guys have seen this or not. A lot of my first period class had not. Does anybody need a moment before we move on? All right, let me show you this. This is pretty neat. I think it's neat. When we were looking for our x-intercepts, we knew we needed to set the equation equal to 0 and solve, right? And I chose to use this version of the equation, but there is another version of the equation. We did a whole bunch of work to come up with this version also. So I could have just as easily used this version and set it equal to 0, and I'm going to do that in the space we have right now, and I'd encourage you to write this down as well. So my other version of my equation, the vertex form, was this. And I could have gotten my x-intercepts by setting that equal to 0 instead. Now I want you to predict, if I were to go through the steps to solve this, is that going to be more or less complicated than the work we did over here for the quadratic formula? What do you think? Gut instinct? Have you ever done anything like this before? All right, this is going to be awesome. Let me show you this. This is, so we know how to solve equations like this, right? What would you do first to start getting x by itself here? Get rid of this. Add 22 over 3 on both sides. Okay, stick with me here, guys. This is pretty neat. (22 over 3). I just added 22 over 3 on both sides. What would you do next? Oop, I'm missing my square. We divide by 3 on both sides, and I'm gonna write it as times a third because that's more convenient for me over on this side. A third times 3 is going to cancel out just the same as division by 3 would. 22 over 3 times 1/3 is 22 over 9. What next? Square root on both sides. Now when we do a square root on both sides and there's an x involved on one side, what do we got to make sure we do over here? Plus or minus, right? Is anybody starting to see where this is going? Not quite yet. All right, so what's left? I got x plus 4/3 over here equal to plus or minus. Now, when I take the square root of 22 over 9, remember you can take the square root of the numerator and denominator independently. I know what the square root of 9 is. It's 3. Root 22 doesn't simplify. And what am I going to do in my final step here? I'm going to subtract 4/3 from both sides. So what do you think? Was that more or less complicated than getting that exact same answer over here using the quadratic formula? You think less? I do too. I do too. If you have something that is in this format, this vertex format, solving algebraically becomes pretty quick process. There's usually a lot less simplifying involved than the quadratic formula is going to require. Now, however, I would say this. If I started here and my only goal was to find x-intercepts, if I wanted to do it this way, I would have had to go through all this step to get it into this form first and then do this. And I would say in that case, that's probably more complex than just going straight to the quadratic formula. But keep in mind, if you ever do have something in vertex form and you're trying to find x-intercepts for it, just set it equal to 0 and solve. And it'll turn out pretty quickly. Especially if you've got whole numbers here, it's a lot simpler if you're dealing with integers. Okay, any questions about that? Last one. You guys are doing so great, and then we'll be done for the week. This is a process that we are going to use over and over and over and over and over and over again this year. So I think this is the first time we've run into this situation in this class, but you've seen this before. I'm thinking as early as back in Algebra 1. Do you guys remember back in Algebra 1 when they... All right, let's wrap this up. Do you remember back in Algebra 1 when you had a problem, they said, please write me the equation of a line that goes through the points 5, 7 and negative 13, 8. You guys remember doing problems like that? And you used your slope formula to figure out what your slope was. It's going to be some fraction. And then the hardest part was finding the b value. Do you guys remember how you found the b value? What we did was we said, oh, I've got my slope. What would my slope be, by the way, for this? It would be 1 over negative 18. So negative 1 over 18. So I've got my slope, negative 1 over 18. The only thing that I'm missing is this b value over here. And how did we solve for that b value? You guys remember what we did? We went back to, yeah, that's it. The key was we went back to one of these points, we plugged it into the formula, or into the equation for x and y, and then we used that to solve for b. Okay, this is going to come up again and again and again this year, where we're going to be given some information that will get us most of the way to the equation that we're trying to write, but we're going to be missing one little tiny piece of it. And how are we going to resolve that last tiny little piece of it? Well, hopefully they're going to give us a point, and we'll use that point to plug in values for x and y, and that will allow us to solve for the missing piece. Okay, so this is exactly that type of problem. We're going to try and write an equation for this thing. What are they telling us? They're telling us the vertex is -1, -3, and then they've also given us this extra point. That extra point is going to be useful to us in a minute, but let's focus on the vertex for right now, because if we have the vertex for an equation or for a parabola, we know the general format can be pretty easily written in this form, our vertex form. And that point, that -1, -3, gives us most of what we need to complete this thing. If the x-coordinate's -1, we know we're going to have an x plus 1 in here. If the y-coordinate's -3, we know we're going to have a -3 out here. The only thing that I'm missing is the coefficient that goes in front of the parentheses here. That's it. I just need to figure out what a is. How are we going to find it? We're going to plug some numbers in for x and y, and then we'll solve for a. And that's it. Now, when you go to do this, you always want to use a point that you have not already used. So we are not going to plug in -1 and -3 for x and y. If you'd like to see why, just try it sometime. If you plug -1 in here, this is going to become 0, and you're going to get an equation that just says -3 equals -3. There is no more a. So we're going to go with the other point here, this x value of 1, this y value of 5. We'll plug those values in for x and y. We'll have a nice simple equation that we can then solve to figure out what a is. That's just 2 squared is 4. And that's it. So this will come up with polynomials. We're going to be taking graphs of a polynomial and trying to write an equation for it. We're going to be able to figure out mostly what the equation looks like, except we're going to be missing this a value that goes out in front. And how are we going to find it? Well, we're going to find some point on the graph, and we'll use its x and y coordinates to help us solve for a. We'll do the same thing with rational functions. You'll see this also pop up in the second semester when we're writing equations for trigonometric functions like sines and cosines and tangents. All right, any questions? You guys are awesome. Thank you for your attention today.